Hey everybody, in this video, I'm going to show you a technique that I use for evaluating trig function values from the unit circle. We've seen the unit circle at this point, and I know that there's sometimes advice to have that unit circle memorized. If you're anything like me, you have a hard time memorizing that many values. So what I'm going to show you in this video is the technique that I personally use to help me evaluate trig function values from the unit circle quickly enough. Especially when you're needing to give an exact value, so you need to have that unit circle knowledge. Please, if you are not familiar with the unit circle at this point, maybe pause and come back to this video at another time. The less familiarity you have with the unit circle, this video may not be very helpful. So just keep that in mind. And again, I am just wanting to point out that this is my thought process. It's not the only way to work with the unit circle. You might find other videos that explain how to do similar deriving, but truly this is just what I wanted to share with students. If you're not following along, no need for you to continue watching this movie or this video, but if it's helpful, great. So to derive the unit circle values, we need to be familiar with the unit circle. Like I said before, if we don't have any familiarity with it, then this is not going to be helpful. So we need to know our sine and cosine values. If we think about our unit circle, and you could reference your notes, and whether you look at the unit circle or you look at the table that we have for our 6 trig functions, but really all of our 6 trig functions are derived from sine and cosine. So as long as we know the values for sine and cosine, which are the ordered pairs, then that's all the values we're going to need. So thinking about the values from the unit circle, we've got 0, we've got 1. We also have -1, so I'm going to do plus or -1 here. If we think about the next ordered pair, we've got 1/2, so also plus or minus. We've got plus or minus the square root of 3/2, and plus or minus the square root of 2/2. Now, from here, we also kind of need to know what these values are associated with. 0 and 1 are the quadrantal angles. Square root of 2/2, that's always going to be associated with some odd multiple of pi/4. It's the 1/2 and the square root of 3/2. Those values I think are the trickiest, and because they're associated with either values of pi/3 or pi/6. Now, I generalize it to just multiples, but obviously if we have, let's say 3 pi/6, that simplifies to pi/2, which is a quadrantal angle. So I am sort of overgeneralizing here, but I think it'll be all right. So with that 1/2 and the square root of 3/2, we do want to think about their decimal approximations. So I'm going to make another point over here. We know 1/2 is equal to 0.5. And then we have square root of 3/2, which if we calculate that, is approximately 0.87. So what this tells me is that a value of square root of 3/2 has a larger magnitude than 1/2. So square root of 3/2 is 0.87, larger than 1/2. So we're going to use this knowledge as we continue through this. We also need to know the sign of each trig function based on the quadrant. If we set up our coordinate grid in quadrant 1, all of our trig functions are positive. In quadrant 2, only sine is positive. In quadrant 3, only tangent is positive. And quadrant 4, only cosine is positive. Now, this also follows from just knowledge of the Cartesian coordinate system. In our first quadrant, both x and y are positive, which again, x and y correspond to cosine and sine values in the unit circle. In quadrant 2, y is positive, but x is negative. So sine is going to be positive, cosine's negative. In the third quadrant, both x and y are negative. So cosine and sine are both negative, and that ratio then for tangent becomes positive. And then in our fourth quadrant, we have a positive x and a negative y. So cosine is positive, sine is going to be negative. Understanding our quadrantal angles, we kind of already talked about this, but our positive x-axis is 0 radians or 0 degrees. And that ordered pair is 1, 0. Our positive y-axis is 90 degrees or pi over 2 radians. And that ordered pair is 0, 1. Our negative x-axis is 180 degrees or pi radians. And that ordered pair is negative 1, 0. And our negative y-axis is 270 degrees or 3 pi over 2 radians. And that ordered pair is 0, negative 1. So, and then again, cosine is your x value, sine is your y value in those ordered pairs. The next thing we want to understand is how the multiples of pi over 6, pi over 4, and pi over 3 create these points along the unit circle. So I'm going to start by just illustrating multiples of pi over 6. And I'm just going to count them off. So pi over 6 is that smaller segment. It's this length. This is 30 degrees. So that tells me that this is 1 pi over 6. And I'm just going to increase that numerator. 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. Now those quadrantal angles are just angles that are going to simplify. So are those multiples of pi over 3. But we can use those equal segments to count off so that if we have something like 11 pi over 6, rather than trying to memorize where that's at, I can simply go, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's my 11 pi over 6. Okay, so now let's look at pi over 4. Pi over 4 is a little bit easier because with pi over 4, we know that those are those like perfect diagonals in each quadrant. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 5 pi over 4, 6 pi over 4. I counted that wrong. 1, 2, 3, 4, 5. Oh no, 6 pi over 4, 7 pi over 4, 8 pi over 4. And that's, again, those perfect, the pi over 4, odd multiples of pi over 4 make those perfect diagonals in each quadrant. The nice thing about those odd multiples of pi over 4, the ones that are not on the quadrantal angles, those ordered pairs are always square root of 2 over 2, square root of 2 over 2. So all you need to know are the signs of the trig functions within each quadrant. All right, and last, let's look at pi over 3. Pi over 3 is bigger than pi over 6, so it's that bigger segment. So from our positive x-axis all the way up to this point, that's pi over 3 or 60 degrees. So there's 1 pi over 3. Here's 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3. So if you're able to kind of visualize how the unit circle is broken down by these multiples of pi over 6, pi over 4, pi over 3, it does help us in how we're going to use all this information to then derive values from that unit circle. Again, before we go into some examples, I do want to point out that I do not have the entire unit circle memorized. I use this all the time to evaluate trig functions from the unit circle very quickly. All right, so let's practice. We want to find sine of 3 pi over 4. So to do this, I'm going to just set up a quadrant, an XY axis. I'm not going to set up a circle because there's no point in me trying to draw out a circle. It's going to be awful. But I need to go 3 pi over 4 units. So thinking about this, I know that here's 1 pi over 4. Here's 2 pi over 4. Here's 3 pi over 4. So my angle, oops. Let me start that over because it did not want to erase nicely. I'm just going to use points instead of lines. Here's 1 pi over 4. Here's 2 pi over 4. Here is 3 pi over 4. There's my angle. And I know, again, at that pi over 4, those perfect diagonals, my ordered pair is going to be square root of 2 over 2, square root of 2 over 2. And now I just need to check signs. Since I'm in the second quadrant, x is negative, y is positive, sine is positive. So that tells me that sine of 3 pi over 4 is square root of 2 over 2. Okay, cosine of 7 pi over 6. So the multiples of pi over 6 and pi over 3 are where things get really interesting, and I really love this practice. All right, so 7 pi over 6, I'm going to do that same thing of trying to count off multiples of pi over 6. Remember, pi over 6 is that smaller segment. So here's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6. So here's my angle. Now, I'm going to create a right triangle with that, just like we would in any other example. Now, looking at this right triangle, what we want to observe, we know that the ordered pair is going to be some value of square root over 3 over 2 and some value of 1/2. Okay, the question is, which is which? This is where knowing the magnitude or that decimal approximation of those two values is really helpful. We know that square root of 3 over 2 is larger than 1/2. If I look at my triangle, my x is longer than my y. So that means my x has to be that square root of 3 over 2 value. And my y has to be the 1/2. And now we add our signs. So I'm going to write this as an ordered pair when I add signs. The x is going to be negative square root of 3 over 2 because we're in the fourth quadrant. Our y is going to be negative 1/2 because we're in the, I just misspoke, we're in the third quadrant, not the fourth quadrant. So both x and y in the third quadrant are going to be negative. Cosine being the x coordinate is going to be negative square root of 3 over 2. So ultimately what I'm going to be doing with any multiple of pi over 6, any multiple of pi over 3, what I'm going to be trying to do is set up that right triangle in my picture to identify which leg of the right triangle is longer than the other. And that's going to assign the value of square root of 3 over 2 and 1/2 appropriately. Tangent of negative 13 pi over 4. Now, you can simplify 13 pi over 4 if you want to, but I'm just going to count because I feel like it's just as easy. And it doesn't require quite as much effort in my brain. So a negative angle, remember, we're going to start moving clockwise or counting clockwise. So here's 1 pi over 4, 2 pi over 4, 3, 4, 5, 6, 7, 8 pi over 4 is going to, or negative 8 pi over 4 is going to bring me back to 0. Okay, so I know I'm on the right track. Okay, so I'm at 8, 9, 10, 11, 12, 13 pi over 4 is going to terminate in that second quadrant. In my second quadrant, any multiple of pi over 4 is going to have those values of square root of 2 over 2. The x is going to be negative. the y is going to be positive. Tangent is the ratio of sine over cosine. Since those values are the same, the signs are just different. This is going to be -1. Sine of 11 pi over 6. Let's change this to 11 pi over 3. I think that was my intent. We're going to make this sine of 11 pi over 3. I don't think we've illustrated how to count the multiples of pi over 3 yet. So remember, pi over 3 is that little bit bigger of a segment. So starting here with 1 pi over 3, here's, let me bring it inside the quadrant. 1 pi over 3, 2 pi over 3, 3 pi over 3 is going to be pi, so I'm in good shape. 4 pi over 3, 5 pi over 3, 6 pi over 3, which is 2 pi. Keep going. 7, 8, 9, 10, 11 pi over 3 terminates here in the fourth quadrant. Now, if I create my right triangle here, looking just, I mean, this is a sketch and it's still giving me a good enough amount of information. Looking at this, it looks like the x coordinate is the shorter one, the y coordinate is the longer one, which tells me that this is my 1/2 and this is my square root of 3 over 2, making the ordered pair positive 1/2. And because we're in the fourth quadrant, remember y is negative, negative square root of 3 over 2. So sine of 11 pi over 3 is negative square root of 3 over 2. Now, when I'm starting to work on this quickly in the middle of a problem, you'll notice I don't draw out quite as elaborate of a picture. A lot of times it ends up being a sketch like this, where I'm like, okay, I can tell my angle is here. That's not that great. I know my angle terminates right here. I sketch my triangle, and then I can see the x is shorter than the y. So we don't necessarily need to have a very elaborate picture for this. The quicker the sketch, the faster this process is. And then that's really what we're hoping to do, is to expedite the process of evaluating these trig functions without having to constantly reference our unit circle.